Hey everybody, welcome to Calc 2. We start off Calc 2 picking up where we left off with the integral in Calc 1. And we want to use the integral, apply the integral to actually do some stuff. And one of the places where we start is finding the area between two curves. Now, finding the area between two curves, it's not really that hard. There's just a couple things that we kind of need to watch out for. All right, well, let's take a look. First of all, let's lay it out. If we have some continuous function, differentiable function, or integrable function, f of x, and it is greater than or equal to some other function, g of x, some other integrable function, on some interval, a, b. So we've got our one function is greater than the other on this interval. Then the area between is the integral from a to b. So we got a definite integral, we're finding an area. Integral from a to b of f of x, our greater function on that interval, minus g of x dx, or f of y, gy, dy, depending on which way we're looking at it, whether we're looking at it dx or dy. Okay, so there's our formula for the area between two curves. It's not too crazy. We just need to integrate the difference between these two guys. Now, one cool thing, we have a rule, right, that says the integral from a to b of f of x minus g of x dx. Well, the integral is well behaved with respect to sums and differences, right? So we can split that apart. The integral from a to b of f of x dx minus the integral from a to b of g of x dx. So we have this rule that says we can split integrals apart. They're well behaved with regard to differences. Now, actually, this affords us two different ways to interpret our area between two curves. So in this way of looking at it, let's say I've got, so here I am, I've got some function f, there's my f, and I've got some other function g, so here's g, and on the interval from a to b, f of x is greater than g of x, yeah? Okay, looking at it this way, what I'm adding up, remember the integral is adding up a bunch of different rectangles where the base, the width of the base is our dx, infinitesimally small or infinitely thin, and the height of that rectangle is whatever that function is inside, right? So here, this f of x minus g of x, this is the height of the rectangles that we're adding up here. So if I think about it that way, what we're looking at is, of course this is blown up, right? But what we're looking at is that difference right there, f of x minus g of x, is the height of that rectangle, and of course the width is dx, right? So we're adding up all those rectangles as we go along from a to b. Again, another typical, oh, I shouldn't write over that. Another typical rectangle, say, would be something like this, right? And again, our height. So we're adding up all these rectangles as we go along, and as the difference between those two functions changes, our height changes. And so if we're adding up all these rectangles, we fill in all that area that's in between those two curves. Okay, so that's looking at it this way, f of x minus g of x. We're looking at the heights of those rectangles. In this way of looking at it, and remember these are two equivalent statements, they're equal. Let's draw a similar picture. Our f is up here, and our g is here, and there's our a, here what we're saying is, okay, take the integral of f of x. Well, that's all of this. Right, here's my f, and here's my g. So the integral of f is all of that area underneath of f, between f and the x-axis, right? Now we're saying take away the integral of g of x. Take away the area that's underneath of g of x, which would be this stuff. So if I have all that area, the integral under f of x, and I take away this area, the integral that's under g of x, what I'll be left with is what I want, the area in between. So either way you want to look at it, doing it mathematically, those are generally a wash, depending on whether they're combinable or not. Maybe we want to split it apart because it's easier to do the integral separately, or maybe it's just some polynomial and it's no big deal. So mathematically or algorithmically, I guess, doing the actual math, those are basically a wash. We can just choose whatever's the convenient way to do it. But conceptually, they give us two different ways to think about what it is we're actually doing, what we're actually adding up. Okay, so that's the formula. Now, one thing to note, or one thing to watch, a warning here, let me erase that. This is kind of the only thing that we really need to be cautious about when we're doing this, is that f of x has to be greater than g of x on that interval for our formula to work. This is our hypothesis, right, and then our conclusion. So if our hypothesis is not true, that is to say that f of x is less than g of x, then our formula isn't going to work. Now, we have another rule. It says if I have the integral of a to b of some function f of x dx, and I have some c in between a and b, then I can split that apart, and I can go from a to c of f of x dx plus the integral from c to b of f of x dx. So I can split integrals apart, right? We have this rule, provided that I have some value in between. And we don't have to worry, right, about the integral from c to c, because the integral from c to c, or a to a, from one constant to another, or to itself, dx, is 0, right? So we have that rule as well. So splitting this apart, it doesn't bother me that I'm counting this c bound twice. That area is actually just adding 0. Okay, so we have this rule that says we can split integrals apart. I'm going to need that if my behavior changes, right? I have to worry about greater than or less than. So, for example, let's say I have some function like this and another function like this. So here's my f, and here's my g, and then we'll go a to b, and then this is some c in between. Say, well, on this interval here, going from a to c, g of x is actually greater than f of x. So I'm going to need to reverse those based on which one is greater. So I'd have the integral from a to c of g of x minus f of x dx. Take care of this piece where g of x is greater, and then I add on to that from c to b, integral from c to b, f of x minus g of x, because on that interval, f of x is greater than g of x. dx. Okay. So that's the kind of the one thing that we need to worry about when we're doing these, is if that greater than or less than behavior switches. Okay. The hard part of these questions generally, or the thing that involves the most work usually, isn't this, because it's just really formulaic. We're just doing the integral and evaluating, subtracting, doing that definite integral stuff. It's kind of formulaic. The real work actually ends up being algebra, because very often we're not going to be given what those bounds are. So that's kind of the first step in attacking these problems, is what are my bounds? You know, if they hand me some problem like, I don't know, I've got some random problem, and I'm meant to find the area between these guys, they're not going to necessarily give me any bounds. I'm not going to know from where to where I need to integrate. So that's usually the hard work, is the algebra and finding those intersections and solving those intersections to find what our bounds are. It's usually the majority of the work in these problems. Okay, so we talked about our warning there. We got to watch for flips in behavior. The hard work is finding the intersections generally. One bonus of this formula is, you know, when we think about integrals, or when we look at integrals as areas under curves, let's say I was looking at the integral from 0 to 2 pi of sine of x, right? Well, normally when we interpret the integral as an area underneath the curve, this area is going to be positive because it's above the x-axis, and then this area is going to be negative because it's below the x-axis. So that total integral, the integral from 0 to 2 pi of sine of x dx, that's just going to be 0, right? These two areas are exactly equal. One's positive, one's negative. They just cancel each other out. So usually when we interpret integrals, we have to worry about the fact whether that area is positive or negative, whether we need to, you know, take the absolute value of that area, or we could, in this case, recognize that these two areas are symmetric, and it would have been just the same to say twice the integral from 0 to pi of the sine of x dx. And that's another way around it, right? But with our formula, it's very nice that we never have to worry about whether the area is positive or negative. The difference of those two areas is always going to come out to be positive, right? If you think about it, if I've got some function up here and some function g of x up here, well, that was the situation we just looked at. That clearly is going to be a positive area. But if I've got some other g of x, say downstairs, below the x-axis, you'd think, well, I got to worry about the fact that this is negative, but you don't, because the values of this function they're going to be negative, and when you subtract, you're going to get f of x minus a negative g of x, which is going to add together and give you a positive value. And likewise, if your f is below, here you're going to have a negative value, but you're going to be subtracting away a greater negative value. In other words, you're going to be adding a bigger value. So again, it'll come out positive. We don't ever have to worry about where the functions are situated relative to the x-axis, or whether those areas are positive or negative. It'll always come out to be positive, which is a nice bonus. The only thing we have to worry about is which one's greater on those intervals. Cool. All right, so let's just look at a couple examples. Let's say we have y is equal to x squared plus 2x plus 1, 2x plus 1, and y is equal to 2x plus 5. Okay. So this is we're asked to find the area between. Okay. So that would be all the information we would actually even need in order to approach this problem. Just need two functions, find the area between them. Okay, cool. Now, I'm trying to set up a to b f of x minus g of x dx. But I need to know if there's which one's greater than which on this interval, or whether there's any switches in it if I need to split things up. Plus, I need to know where these intersections are in order to build my bounds. So very often, the first thing I'm going to do is go to my handy dandy calculator and graph these bad boys. That way I can at least get an idea of what's happening, what the situation is. I can get a picture, and we can all, cheat and use intersections and things like that to find the bounds. But usually we don't need to do that. But more or less, just looking at the graph to figure out what's going on. This is a parabola. It's not stretched or squished. It's not narrower or wider and then the parent, and it opens upward. It's shifted over, so it looks somewhat like that. And then 2x plus 5, linear function, positive slope, it's lifted up. So it looks something like that, more or less. Okay, so the area between these two guys is this. That's what we're asked to find right here. Now it looks as though on the entire interval, from this intersection to this intersection, we still need to find those. But in the entire region where there's area bounded between them, the linear function is greater than the parabola. So there's no switching of behavior. I don't have to worry about breaking the interval. The whole thing, there's a single behavior. The linear function is greater. So that's what I'm going to call f. And then my parabola is lesser on that interval, so that's my g. Okay, so let's see. So far we've already got the integral. We're going to have our linear function, 2x minus 5, subtract our parabola function, x squared plus 2x plus 1 dx. Okay, so here's my f of x, the greater function, and there's my g of x, and I'm taking their difference. All right, and let's see, the only thing that we need left are our bounds. Now, the bounds are given by the intersections of those two functions. So I just need to set these two guys equal and solve. X squared plus 2x plus 1 equal 2x plus 5. All right, x squared, oh, does that go? Oh, that's pretty. The 2x's subtract, so we've got minus 4 is equal to 0. This is a difference of two squares. That factor is real nice. X plus 2, x minus 2. So we've got x is equal to plus or minus 2. Fair enough. That's easy. So negative 2 down here, positive 2 up here. Double check that I didn't make any, yeah, the 2x's go, subtract 5, difference of two squares, beautiful. Okay, so there's our actual setup. Again, most of the work was doing the algebra, finding the intersections and factoring and doing all that business. But now we've got that set up. I'm going to move it up here. Let's see, we have the integral from negative 2 to 2, negative x squared, 2x minus 2x, those are 0, negative 5 minus 1 is minus 6 dx. Since these are polynomials, I'm just combining them together rather than doing those integrals separately and subtracting. So that it'll just be straight power rules, right? Let me double check myself here. That's a negative, yes. 2x minus 2x goes bye-bye. Negative 5 minus 1, negative 6. Okay, beautiful. All right. So there we've just combined our like terms and simplified to make life easier. Now this is a polynomial, so it's straight up product rules. Negative, or power rules, x cubed over 3, add 1, divide by the new power. minus 6x, add 1, so x to the first divided by the new power, evaluated at 2 and negative 2. Okay, remember this is our fundamental theorem where we take the antiderivative and evaluate at b, subtract, evaluate at a. So I'm going to evaluate it at b first. Negative 2 cubed over 3 minus 6 times 2. There's my eval at b. Minus, now I need to eval at a, negative 2 cubed over 3 minus 6 times negative 2. Okay, we're going to have a lot of sign flipping going on here, so let's see what we got. This is a straight up 8, so negative 8 over 3 minus 12. Okay, those are legit. Now let's see, this is going to be minus. This is negative 8, so negative is positive 8. 8 over 3. Minus, so that's plus a 12. And it looks like we have negative 8 thirds minus 12 minus 8 thirds. Have I done something wrong with my signs here? I must have done. That's coming out negative. What have I done? It's negative, positive, minus, positive. What have I done? Hang on. I have to pause it.